graduate level course on biochemical engineering, and this is a course that I and Professor Sudarshan Yogi are going to teach together. And what we'll try and do is give you a sense of the coupling between biochemistry and transport and reaction as applied to chemical engineering. So before I go into the details of today's lecture, what I'll try and do is give you a sense of the overall outline for the course. Let me try and make this larger. So these are some of the things that we're going to cover. For example, basics of biology, overview of biotechnology, diversity in microbial cells, cell constituents, and so on. So essentially, to give you an idea of how cells work, and in the earlier course that we did on transport processes, we had a sense of how cells work and what are the essential ingredients of the cell membrane, and so on. In this course, so what is the major difference between the earlier course and this course is that there we concentrated a little more on the transport phenomena. Here the emphasis is more on reaction engineering aspect of it, but of course you cannot deal with reaction engineering as separated from transport phenomena. So we are going to look at the coupling between the two and the whole series of biochemical reactions that happen, how cells respond to it. That is at the cellular level, and as always our emphasis is on how to move from one scale of analysis to another. So we can move on from the cellular level, that is a micro scale, to the mesoscale, to the macro scale. So if you look at this, so at the cellular level, for example, so we start the course essentially at the cellular level, where we talk about basics of biology and so on, and the kinetics of enzyme catalysis, which is the chapter that we're going to start today. And then we'll look at something like immobilized enzymes, and I'll talk about immobilized enzymes when you come to it a little bit, and talk about metabolic pathways and so on, and microbial growth models. Then we go to a larger scale where we deal with, when we deal with the microbial growth, the larger scale of where you talk about of not just one cell but a cluster of cells and how these cells grow. So now you are moving on from the micro scale, which is the scale of a single cell, to the macro scale, which is the mesoscale, sorry, which is the scale of a cluster of cells, and so on. So and then the next step we go on to design, analysis, and stability of bioreactors, which is obviously the macro scale, right? So now we look at not just the reactor design, but when you use these biochemical reactions, when these biochemical reactions happen in the reactor, what kind of dynamics it generates. And these are pretty interesting dynamics and different from the kind of dynamics that you would see elsewhere. When it comes to microbial growth, for example, we'll look at some of the growth models, the stochastic and the continuum models of microbial growth. And why this is important is because when you are doing cell culture in the lab, right? So some of you might be doing that cell culture in the lab. When you are doing that, it is important that you figure out how cells actually grow, and what we'll learn is we'll do some models of cell growth and try and understand how cells actually grow, and then apply those to the biological reactors or the bioreactors, those chemostats. One of the important things and interesting things actually that we are going to do is kinetics of receptor ligand binding. So what is receptor ligand binding? It turns out that most of the physiological processes, we did some of the transport things before, but the reaction part of it, many of the important physiological processes are dictated or governed by reactor ligand binding. Okay, so so they are dictated by or governed by reactor ligand binding. So the reaction between a reactor and a ligand is a necessary ingredient, and some of you actually are working on that. So it's a necessary component of not just how cells work or function in day-to-day life, but also in diseases and therapy of diseases also. And a little bit of regulation of gene expression and byproduct recovery, which Professor Yogi is going to do. So let me go through the books that are involved and that you might want to look at in this course. So the first book is the most important book, Biochemical Engineering Fundamentals, by J. Bailey and D. F. Wallace. This is one of the most classical books of Can you see that on the screen, or do I need to increase the size? Okay, so this is one of the most classical books of biochemical reaction engineering. Bailey used to be a faculty actually in the graduate school I went to, and he's one of the most well-known people in biochemical engineering. So if you want to buy any book, and if you're interested in buying any book in biochemical, this would be the book to buy, and look for references. The other important books also are by Blanche and Clark, and this is Doug Clark from Berkeley, and by Process Engineering by Schuler and Kargi. That's also a nice book as well. The last book that I'm going to just teach one chapter from this book, the suggested reading that is there, Transport Phenomena and Biological System, is by Trusky, Yoon and Katz. This is a pretty expensive book, so I don't suggest buying that, and I'll give you the notes. We'll do the things in the classes so you can take notes. But if you're interested, you can buy that as well. So these are the 4 books, and between these 4 books, everything that we'll do in this class are there between these 4 books. Okay, so let me now give you a sense, because this is a lecture by lecture thing. So let me just give you a sense of some of the lectures that we're going to do. I think Professor Niyogi has started, because 2 people are teaching this course, so I just want to show you how they're split up. So Professor Niyogi is going to teach the basics of biology and the overview of biotechnology and microbial cells and constituents of them. I'm going to start today with biochemistry and thermodynamics of enzymes, and the next class tomorrow we'll do the kinetics of enzyme catalysis, and followed by regulation of enzyme activity, competitive, non-competitive, and inhibition, and so on. Then we move on to immobilized enzymes and heterogeneous enzyme catalysis. What are immobilized enzymes? Enzymes, to start with, let me give you a very quick wrap on this. Enzymes, to start with, are catalysts, right? These are essentially catalysts that catalyze biochemical reactions. So in chemical engineering or chemical reaction engineering, you have catalysts that catalyze normal chemical reactions. Here they just catalyze the biochemical reaction. So that's a major fundamental difference, hardly any difference. What can you think of? What are immobilized enzymes? What could be immobilized enzymes? Because one of the things, the hint that is there in number 10 is enzyme immobilization and heterogeneous enzyme catalysis. So what can you?
Certain reactions, during reaction, enzyme will inhibit it.
No.
Not move.
Right. So the enzymes that we talk of initially are essentially liquid phase enzymes that are there in the liquid phase, and then they dissolve or are soluble in the liquid, and then they go and the substrate comes to them and they help in reaction and so on. So immobilized enzymes, as the name suggests, and it's very straightforward, are enzymes which are not moved, which do not move. So how do you achieve that? What you do is you kind of restrict them to a matrix, and I'll show details of that when we go to that. So we'll kind of restrict them to matrices. Certain matrices, kind of entrap them in certain matrices. And why are these immobilized enzymes important? See, I'll give you a simple example. When you have, for example, indigestion, or you just ate something heavy and you want to get some digestive medicines. So what are these digestive medicines? They are enzymes, right? Be it a gelycol or carmozyme or whatever. These are essentially enzymes which help in the digestion process. So there are 2 kinds of these medicines that you take. Some are liquid medicines and some are tablets, right? So that is an example. So the liquid medicines that you have are normal enzymes in the liquid phase, which go and they work faster a little bit, and tablets are immobilized enzymes. So you have this all kinds of tablets, Pudinara, Gelucel, all kinds of these. So these are essentially immobilized enzymes in a encapsulated form. They take a little bit of time to dissolve into the system and to work, a little bit more than the liquid phase enzymes, but the advantage of these immobilized enzymes are that you can take them along with you, right? Wherever you go, they're mobile. So though they're called immobilized, there's something that you can take them along with you if you want. So we have to understand the kinetics of that, and the coupling between the kinetics and the transport of that, which is a lot more complicated than normal simple enzymes, liquid phase enzymes. Why is that? Why is it? The answer is right there in front of you. So yeah, because these are heterogeneous systems. So when you're talking of liquid phase enzymes, these are homogeneous systems. whereas when you're talking of solid phase enzymes in immobilized form, these are heterogeneous systems, and therefore you have to understand the heterogeneous catalysis and coupling between heterogeneous catalysis and reaction, which is a little more complicated thing. I'm not sure if you have studied. Have you been taught that in reaction engineering? Probably not. Okay, so we'll go into the details of it a little more, and simultaneous diffusion and reaction and all these things. So you know, some of these lectures 12, 13 and so on are about that, and then major metabolic pathways and biosynthesis Professor Neogi will teach. Then I'll go over to microbial growth. So essentially, when you try to in the lab, you know, some of you at some point of time might want to incubate cells, right? So what is the process of that? What is the dynamics of that incubation? What are the ingredients that are necessary? So you start with 1 million cells, for example, and by the end of one day you want to have 2 or 4 million cells. By the end of 2 days you want to have 8 million cells, and so on. So that is the way you grow cells, right? Why do you grow cells this way? Because you want to mimic in a way the growth process, cell growth process in living systems, right? And also because you need these amount of cells to do the experiments. So when you need these cells to do the experiments, so how do you achieve that cell growth? A. B. What are the ingredients of the cell growth? B. C. What are the kind of reactions that happen during the cell growth? And D. What kind of models you can come up with, both continuum and stochastic, to try and quantify this cell growth. Okay. So these are the aspects that we're going to look at over here. Now once we have looked at cell growth, now when these cells grow, after these cells grow, or when these cells are growing, both cases, you can engage them in biochemical reactions in reactors. So these reactors, you know, these are called chemostats. Chemostats are nothing but CSTRs, continuous stir tank reactors. So, but then in the biological framework, in the biochemical framework, you know, parlance, they are called chemostats. And so we'll try and understand the dynamics of it, the design of it, and some of the pretty interesting things we will do, which you probably have not done in other courses, is the stability analysis of bioreactors. Okay, so and substrate inhibition and multiple steady states and so on. And then, as I said, we'll go on and do enzyme, you know, the receptor ligand binding, which is also a pretty interesting thing, because one particular disease that we are going to concentrate on, you know, we are going to talk about the process itself, but with the example of one particular disease, which is, I'll give you a hint and you have to tell me the name of the disease, which is very common in India. It seems like one of the 50% of the people who are suffering from the disease or something like that are from India. So and it has to do with can you tell me some names first and then I'll give you some hint? Huh? Tuberculosis? No, 50 not so many people in India suffer. This is a very common disease, and this is more of a middle class disease, you know, people. Huh? What is that? Diabetes. Not diabetes, but you're close. What is the other disease? Something to do with lipids? Something to do with lipids? Fats? Obesity. Huh? Not obesity, but yes, it is called, the scientific name of the disease is familial hypercholesterolemia. Okay, have you heard of it? Hypercholesterolemia, high cholesterol. You've not heard of this? Yeah. So it's called familial hypercholesterolemia. And why is it called familial hypercholesterolemia? Because the familial part is because it's a family thing. So we will try and understand the effect, you know, the effect of gene expression and so on this. So it's familial, so it's transferred from, it's a genetic disease, it's transferred from one generation to another. And hypercholesterolemia, hyper means extra, and cholesterolemia is extra cholesterol. So anyway, I think what we'll do now is let's move on. So this is just wanted to give you a sense of the whole thing, and let's move on to the lectures. So you know, so as I said, that enzymes essentially are you know, proteins, RNAs or DNAs that catalyze a biological reaction. So the essential function of enzyme is to catalyze a biological reaction, and there's a huge range of enzymes that work in sync with each other in the human body, and without these enzymes, the human body as you know it would not function. So they form a very integral part of the system. And some of you who are working in biological systems, you'll know this. It turns out these enzymes catalyze the rates of biological reactions by 10 to the 4 to 10 to the 12 times. So if there is no catalyst, and if there is catalyst, so the comparison between them, so when you put an enzyme in there, it catalyzes 10 to the 4 or 10 to the 12 times the rate that in the absence of catalyst. And as I said here, one of the points that are noted here is that most important biological reactions do not occur in the absence of enzymes, because these enzymes, even if and trace quantities of them really work, so you don't need a lot of them actually. A very important thing about enzymes, especially in the human system, is their specificity. Okay, and what I mean by specificity is that these enzymes are specific to reactant molecules. Okay, so you want one set of substrates only, or not one or maybe two sets of substrates only to react with that enzymes, and that's why they are called specific. So unless these enzymes are specific, there is no point in putting them, because see, you might have a host of thousands and millions of reactions occurring in the human body. So you need one set of enzymes to work for one set of reactions, otherwise there is going to be complete chaos. And how that is ensured is that the substrates have high interaction, specific interaction or affinity, high affinity with that particular enzyme, and I'll show you in a minute how that how that really happens. The high affinity finding follows enzymes to function effectively in a solution containing a large number of biological molecules at low concentration. So because it's very specific, so even if you put a little bit of enzyme in a large amount of solution, the actual concentration of the enzyme is very low, but as a result of the fact that it is very specific, it works. So specificity is the most important thing in enzyme activity. And then there is something like regulation of enzyme activity. So you may not want a lot of enzyme working, or working at the same time. So for example, in catalyst activity also, some of you, if you worked with catalyst, you know that you need to control the catalyst activity, right? So you don't uninhibited catalyst activity. So just enzyme is a catalyst. So there are ways to control the enzyme activity, and the body finds its way. And what we'll study in this part of this course is how these enzyme activities are regulated. So that's called regulation of enzyme activity. So what we'll study is how these enzyme activities are regulated by the human body and how we can mimic that. And there are ways to regulate these enzyme activities externally also, because once we understand what the process of regulation is, and once we quantify, there are ways to give inhibitors to regulate these enzyme activities. You see what I'm saying? So the body itself does it internally, but once you understand the mechanism of this regulation, you can do that externally as well, right? So that is another thing, and so you use cofactors and so on, and we're going to study that. So now let's come to the question of the biochemistry of enzyme function, and this is essentially what we're going to study in this lecture. So how do these enzymes work? And after we have done biochemistry, we'll move on to the thermodynamics of it. What I want to do is, let me show you some pretty pictures. So these are pictures of some of the enzymes, few enzymes. So this is what you see on the left, top left corner. This is catalase, and what you see here is a glyceraldehyde and 3-phosphate dehydrogenase, another enzyme. This is a human P50 enzyme. And what you see is essentially these bunch of RNAs, DNAs and proteins clinging together and forming these ribbon-like structures. And so if you go back now, what happens now, I hope you saw this, so I'm going back to the older slide. So now to the understanding of what really happens. So enzymes catalyze biochemical reactions following binding. So essentially what happens is the enzyme is there, and there is something called an active site. So look at this picture here. So this is the enzyme. The yellow thing is a schematic of an enzyme, and what you have is called an active site, a part of the enzyme which is known as an active site. Just like in adsorption, you've studied this in absorption also, right? There are active sites for adsorption. So what happens, the substrate comes and binds to that active site. Okay, it's a very simple thing, but there are other complications that come in at some point of time. So so once it binds, once the substrate binds, then it starts to function. Now if you look at the geometry of it, can you make some comment on why this geometry is like this, of the active site and the substrate? Specificity, very good. Do you get what he said? See, this is like a lock and key mechanism. So look at the structure of the substrate and the structure of the active site, and they kind of fit into each other very appropriately. So that is the one that the stereochemistry is the one that ensures the specificity of the enzyme. Now, is there a way? So I think if you do this if you understand the stereochemistry of the process, is there a way to say an enzyme is meant for substrate 1? Is there a way that I can allow substrate 2 to react with the enzyme? What is that?
Change the stereochemistry of the system.
Absolutely. To mimic the stereochemistry, so I design my substrate 2 to mimic the stereochemistry of that. And I think one of the examples I gave you once was that the morphine and the heroin thing, that that is what is, the blood-brain barrier is there, so which cannot be otherwise overcome unless it couples with some substrates, some enzymes. So what is done, what doctors do is that they try to come, the medicos, they're trying to come up with these morphines which have the same stereochemistry as the heroin, and that can cross the blood-brain barrier. So you allow morphine also to cross the blood-brain barrier by mimicking the stereochemistry of that. So this is one of the things we can do over here. So you have the substrate 1, and if you want substrate 2 out there to bind to that, then you mimic the stereochemistry of substrate 1, make it look like, so it's like coming up with a false key to the lock, and you want to enter the sneak in. So an active site interacts specifically with the substrate, providing appropriate orientation. So this has to do with the stereochemistry of the reacting molecules, and it alters also the electrodynamic environment to make the occurrence of the reaction favorable. Okay, so I'll come to that. When you come to the thermodynamics part, you will understand this a little better, that how it alters the electrodynamic environment to make the to facilitate the reaction. And in terms of biochemistry, there are specific amino acid side chains that serve as catalytic agents, facilitating bond breakage and formation of the product. And what we do is, there are several molecular biology techniques such as mutagenesis and so on that are used to determine the specific structure function relationship, and this is pretty important. The reason is that, see, there is a direct relationship between the stereochemistry of the function structure of the enzyme and the function it performs, right? And how an enzyme facilitates a particular reaction is also governed or influenced by its structure. Okay, so and that is why it's very important to understand the structure function relationship. And if you want to, one of the things that are important in the human drug preparation and delivery is to come up with some important enzymes which can govern or which can influence biological physiological processes. Okay, so unless we understand the structure function relationship of existing enzymes, so that is what I was trying to say, that if you want to mimic the activity or the function of a particular enzyme that is already existing and come up with something new and innovative, you have to understand the structure function relationship, the very nuanced relationship that is there between structure and function of that enzyme, in order to be able to mimic that, right? And much of modern biology and some people said that recently that it's well known that this century is going to be probably the century of biology, and if you want to do that, you have to understand the human system or the system that is there in nature very, very well. What I mean by that is that what we have to do is do reverse engineering, okay, which is understand the engineering of the human body or the physiological system in itself, and then try to mimic that. Why is that? Because the human system has gone through 4,600 million years of evolution, so starting from when life started itself. So you cannot have anything better than that. In one lifetime, in 100 years, 50 years or 100 years of industrial age, we cannot better that. So the best thing we can do is try and understand the way the physiological system or a human system works, and then mimic it. So that is the reason we need to understand the structure function relationship. That is not something we are actually essentially going to do in this course, but I want to stress the importance of it to you, so that if at any point of time you're interested, you can go and study that. So some of these, for example, why these structures are like this, where are the active sites, and what essentially happens when you go into the biochemistry. These are things that are beyond the purview of this course. This is more an engineering course, but at any point of time, if this is good enough to induce your interest in it, so you might want to take some other course on this, and there are some in the chemistry department. Okay, now let's in the next part of this, let's talk about the thermodynamics of enzymes. Okay, so I would have liked you to participate on this a little bit, but anyway, so it's out there in front of you, and there are not too many questions I can ask once I've shown you the slides. So essentially, you know this, right? That if for a reaction to be thermodynamically possible, its delta G, its gives free energy change between the initial and the final change, final state has to be negative, right? Without that, we cannot have a reaction. Now, if that is not possible, then there is no role of enzyme. Okay, let's be very clear about that. Enzymes cannot change the Gibbs free energy delta G for the system. Okay, the delta G for the system, the Gibbs free energy change for the system is between the initial state and the final state, and the energy and the enzyme has no role in it actually. What the enzyme does is what you see here in the picture. Okay, so if A plus B is to go to C, essentially it has to form an activated complex, right, AB plus. And the problem with this is that there is a big threshold that is there. So you have to go reach the mountaintop and then dive in, right? Even if your delta G is less, but you need a threshold energy to cross that energy threshold barrier. Okay, what the enzyme does, and now we will show that, maybe if not in today's class we can show a little bit, but very soon, I mean, in the following classes we'll do that. What the enzyme does is essentially create a different complex. So you A and B together form a complex AB plus, an activated complex AB plus, which has a certain activation energy. So this is your activation energy. What the enzyme manages to do, it binds to the active sites of the substrate, or the substrate rather binds to the active site of the enzyme, and it forms a different complex, which in this case is written as AEB plus, E being the enzyme, and this complex has a much lower threshold energy or barrier to be jumped across to go to C. So that essentially is the thermodynamics of enzymes. So so it turns out that, however, even for reactions with small delta G, they are often limited by the energy barrier, and you cannot perform these reactions without catalysts. So there are two kinds of things, and I mentioned this in the first slide itself. There are two kinds of possibilities. One is the reaction occurs without the enzyme, and you use the enzyme to catalyze it, to hasten it, or to accelerate it. There is another possibility where the reaction does not occur at all with the enzyme. Okay, why is that? Thermodynamically it might look okay, but the point is that so delta G could still be negative for that reaction. So the reaction delta G, what does delta G negative tell you? Delta G negative does not tell you that the reaction is going to occur. What it tells you is that the possibility of the reaction to occur, that it is possible for the reaction to occur. If you look carefully and go back to your thermodynamics book, that is what you will find. It does not say that the reaction is actually going to occur. So it just ensures that the possibility, that it is feasible to conduct this reaction. Now there are plenty of reactions where the delta G could be negative, but the threshold, the initial threshold from the initial state to the complex is so high that the reaction does not occur, okay, unless you put in an enzyme. So that is a very important thing, and many biochemical reactions are like that. So enzymes, how to do it, and as I said, this is just a summary. What is written here is just a summary of that. So enzymes provide an alternate reaction pathway that produce an activated state of the reactants with lower energy barrier. As a result, the rate of reaction is increased significantly, but the overall change in the energy between the reactants and products remain the same, right? Is that clear? Is there any question on this at this point? Okay. So we'll start a little bit and do a little bit of the kinetics of enzymes. So essentially, if you have a reaction like S going to P, S being the substrate and P being the product, right? So without an enzyme, the reaction is very straightforward. We are just looking at a simple reaction. The reaction is very straightforward. It is S going to P, reversible. By the way, let me ask you this question at this point. So if it were not a reversible reaction, S going to P, if we put a reversible sign there, what does it mean? If I just put S going to P as a irreversible, just one-sided arrow, what does it mean? Just S going to P, if I put a reversible sign, what does it mean? Does it mean anything? Or That's
Only
right. Very high what?
Backward rate of reaction is very good.
Right. So if you put an irreversible sign, what it means, it doesn't mean that the reaction is irreversible. It only means that the forward rate of reaction is very, very high as compared to backward rate of reaction. See, there are no reactions which are completely irreversible. When we put, this is something that you probably have not learned. When you put an irreversible reaction, you tend to think that the reaction is irreversible. That's not true. There are no reactions which are completely irreversible. Okay. When you put a forward rate of reaction, it means that the forward rate of reaction, when you put a one-sided arrow, it means that the forward rate of reaction is very, very high as compared to the backward reaction, and that's why it appears in most all practical cases, with or without catalyst, it appears to be irreversible. Okay. So here when you come to, so this is E is enzyme, S is a substrate, excuse me, P is the product and product. And what happens is that then the substrate, let's go back to this. So the substrate goes and binds to the active site of the enzyme, and then you have the activated state. Okay, here A. So if you have A plus B together, so what happens is that there are two substrates that are there, and the enzymes go and bind with them. So there could be a substrate here, and there could be another substrate on the other side, and the enzyme kind of fits into the active sites of both of them together and forms this complex AEB, which then later dissociates to give you a product and your enzyme. So the enzyme being a catalyst, this is very straightforward, but it's an important fact to note, because people make mistakes sometimes, that enzymes being a catalyst, it's not consumed in the reaction, right? It just accelerates the reaction, but it's not consumed in the reaction, and it affects the rate of reaction, but it does not have any effect on the equilibrium. Now, if I ask you, for example, two things that we do in what is one of the major difference between, say, thermodynamics of this is thermodynamics, right? The thermodynamics of reaction and the kinetics of reaction.
Thermodynamics talks about feasibility, and takes
Feasibility, and its feasibility, of course, but apart from feasibility, what else?
Thermodynamics talks about the equilibrium constant.
Both, yeah. Both the feasibility, that is whether delta G is less than 0 or not. So whether the reaction is possible, A, and B about the equilibrium state, final equilibrium state that is reached. Kinetics deals with the dynamics of the process. Okay. So how fast that is going to be there, and these are concepts that have to be very clear in your head. For example, when you're dealing with you do courses like thermodynamics and heat and mass transfer and so on. So what again, what is the difference between thermodynamics when you do it the way you do and heat and mass transfer? The same difference. That is, in thermodynamics, you are talking of the equilibrium state. You're talking of the final state that is being attained. Whereas all kinds of transport processes that you do, heat, mass, momentum transfer, are about the process, about the dynamics of the process. Okay, so thermodynamics time is not a variable. Okay, the variable that is discounted in thermodynamics is time. Time is not a variable in thermodynamics, where in other processes thermodynamics time is a variable. So even here, when we talk about kinetics, time is a variable, and you have to talk about the dynamics of the process, and you have to find out how the rate of reaction is increased or decreased by enzymes. Because see, at the end of the day, why are we using these enzymes? A, to decrease the threshold, okay, so that the reaction actually occurs, and B, also to accelerate the reaction. So these are two different issues, and in order to understand how it accelerates the reaction, you have to look at the dynamics of the process. So that is what we are going to do. I'm not sure you can finish this today, but let me start with it at least for the next 5-10 minutes. Okay, the class is till 9:25, right? Yeah. So so the kinetics that is used, and I don't want to rush you through this, but just give you a sense of it, is known as Michaelis-Menten kinetics, and I'll talk about this a little bit. These were discovered by two gentlemen, Michaelis and Menten, separately, I think in the early part of the 20th century, some early part of the 20th century. I can give you the number in the next class. It's in the book, Bailey's book also. So so what is important, this is the most used kinetics, and they became really popular people, because this turned out to be the most used kinetics in most of reactions. The reason is that if you look at this kinetics, can you comment on equation 1 that you have over here? This gives the rate of reaction. Okay, so these are for most enzymes. What it says, for most enzymes involving single substrates, experiment shows that the rate of consumption of the substrate is given by Rs is Rmax Cs over Km plus Cs. What is Cs? Cs is a concentration of the substrate. Km is a known as the Michaelis constant or Michaelis-Menten constant, and Km is the value of Cs when Rs equals half of Rmax. Rmax is the maximum reaction rate that it is going to attain. Okay. Can you comment on the nature of this? If I am to plot Rs versus Cs, that is the reaction rate versus concentration, that is how you figure out what the rate order of the reaction rate, right? So if you have a first order reaction, you know, it's the straight line. If you have a second order, it's quadratic, and so on. So can you comment on the nature of this? No, but what is what is the nature of the plot? That is written here. You don't, huh? Convex, no. Initially linear. Okay, so that is written there also. So I'm coming to this. Okay, let's look at, so whenever you are trying to understand or quantify something complicated, the strategy, the engineering strategies, and this you can hammer down to your head. The engineering strategy is to look at the two asymptotes. Okay, the smallest and the largest values. So that will give you what will the asymptotes give you? The bounds. It's called the bounds. The asymptote will give you the bounds of the curve. Okay, so if you look at this, for example, in here, so let me go through this one more time. So Rs is the rate of disappearance of the substrate or the rate of reaction. Rmax is the maximum rate of reaction. Cs is the concentration of the substrate. Km is the Michaelis constant, like a rate constant, and Cs is the substrate I told you. And the value of Km is evaluated by this. So Rs equals Rmax over 2. So at Rs equals Rmax over 2. So if you put Rmax over 2, then the value of Cs you get is that, or you know, equals Cs at which Rs equals Rmax, whichever way. So you find the Cs at which the rate becomes half of. So if you're performing an experiment, you're trying to measure the rate constant, the rate as well as the concentration. So you measure the concentration, measure the rate at that particular concentration. How do you evaluate your Km? The simple way is that you figure out where it goes to the maximum, and then half of that maximum. Let me show you some plots. Yeah, it's here. So this is how the plot looks like, and so this is your Rmax. So you figure out that when this is Rmax is say 22 or something, then at what value of Cs, okay, at what value of Cs the reaction rate is half of the maximum. That is your Km. Okay. Now, okay, so here we are. So these are the two asymptotes of the problem. This asymptote and this asymptote, and the two asymptotes. Let's go back to the two asymptotes and try and understand that. So for Cs much less than Km here, if you look at equation 1 for Cs much less than Km, what happens is Cs goes away from the denominator, but it stays in the numerator. Okay, so Rs is given by as Rmax Cs over Km. Fine. So this looks like a first order reaction, right? So as a result, obviously it's linear. So if you look at the plot here, so look at this. So in the small range, Cs being very small, it looks like a first order reaction. It's a linear curve. Okay. What about this? In the other range, that is Cs much greater than Km. So Km goes away from the denominator, Cs remains, Cs in the numerator as well. So you get Rs equals Rmax. Fine. So this is a zeroth order reaction. So the two bounds of the whole reaction is zeroth order and first order. Okay, which means that what is the order of the reaction? Fractional order. Okay, the order of the reaction. So it's bounded by the zeroth and the first order, and so this is how the curve looks like. Okay, and what we will do is we have just a couple of minutes, I think, because at this point I am not going to the analysis today. What we will do is we will resume with the analysis tomorrow. So I just give you a few minutes. If you have some questions on the whole thing, you can ask me. So let's walk through the thing. So some of the things about this, let me summarize for you what we did. Some of the things that you need to remember is that enzymes are catalysts. They have two roles. One is to reduce the threshold of the energy and make the reaction happen, because there are lots of reactions that wouldn't happen. The energy barrier, the threshold energy barrier is so high that there are plenty of reactions in the human system that would not happen without enzymes. So they have two roles. One is to lower the threshold so that the reaction happens, and B is to accelerate the reaction rate. So some of the numbers that I gave here are 10 to the 4 to 10 to the 12 times it accelerates the rate of the reaction in the human system, and there are plenty of reactions, as I said, which do not even happen without the presence of enzymes. Now, one of the most important things about enzymes is its specificity. Okay, so substrates, because there are so many substrates, and you have a limited number of enzymes. So if all substrates start to react with all enzymes, what will happen? The enzymes will be depleted, and the particular reaction that the enzyme is meant for, that won't be available for the reactant, right? So there is a sense of specificity. So enzymes are specific. How is the specificity enacted? Here you can see. So the enzymes and the substrate has a sort of a lock and key mechanism. Okay, and if in most cases it's not that, this is a simple example where an enzyme is binding to a single substrate, but in most normal cases what happens, there are two substrates, right? And the enzymes bind in a way that it binds to both of them, or to one of them when the one is bound to the other. You see what I'm saying? So this substrate that you see over here either is going to bind to two of the A and B together in a way that a part of it fits into the active site of A and a part of it fits into the active site of B, or in a way that it binds to one of them. And then these are specific amino acid side chains and catalytic agents, facilitating bond breakage and so on. And I showed you some pictures of that, and this is the thermodynamics of it. We went through that, and delta G has to be less than 0 for a normal reaction, for a reaction to be feasible. And the enzyme forms, what it does, it forms a complex which is much lesser threshold than A plus B, much lesser complex than when A plus B is formed, and then we went to the kinetics of it. Just a second. So is there, I think some of you would have to leave because you have classes. So can you, if there are any questions, let me address them at this point of time, and then there will be some other things I can talk about. I think it would be hard to start the next section, which is the derivation of the Michaelis-Menten kinetics today. So what I'll do is we'll start with this tomorrow in tomorrow's lecture, and if there are any questions, a couple of minutes we have, you can ask, and otherwise you may leave. And okay. Okay. So what I'll try to do is try and summarize one more time what we had been trying to do today, which is that enzymes are essentially catalysts, biological catalysts that do two things. One is they lower the threshold energy, and so that a reaction can occur. And if I go back to this slide, as I said, that if you have a reaction of A plus B going to C, the reaction has to go through through an activated complex AB plus, and a threshold energy is needed to cross the activation energy barrier, and if that complex that is formed is A plus B, and the product that is formed is C from there. But there are many reactions where this energy barrier cannot be overcome, and what the enzyme allows us to do, it allows us to form this complex AEB plus, where E is the enzyme, A and B being the two reactants, and which has a much lower activation energy barrier, which could be crossed easily. The delta G remains the same of the whole process. It has to be negative. So that's one thing, and the other thing is that, you know, in the process it accelerates the rate of the reaction. So essentially it provides an alternate pathway that produces this different activated state, and as a result of that the rate of reaction is increased significantly, but overall changes are not there in the energy and the both in the energy and in the products that are formed. So as one can understand from this very clearly, the enzymes do not take part in the reaction. So if you look at the kinetics, the basic kinetics of the enzyme, what happens is that the enzyme E reacts with the substrate to form product P, and the enzyme E is again re-released, which means that it does not take part in the reaction. So when you are looking at the reaction overall, the enzyme E does not take part in the reaction, but in the next few lectures we will show that how what are the steps that happen in between these E plus S giving P plus E. There is a whole, you know, whole network of steps that happen, and we will try and expand on that and try to show how the enzymes actually participate in the reaction, but the net effect is that it looks like it doesn't participate. So it accelerates the reaction, but it's not consumed in the reaction, and it affects the rate of reaction, but it does not alter the equilibrium. The reason for that, equilibrium is guided by the thermodynamics and the delta G of the process, which remains the same with or without enzyme. What enzyme does, it changes the dynamics of the process, okay, and activation barrier. So you know, the final wrap up on today would be that what is the kinetics that enzyme follows? The kinetics that enzyme follows is known as Michaelis-Menten kinetics. It's a very well known kinetics, and what it does, the kinetics says, is that the rate of reaction, so when this reaction between of E plus S giving P is there, what is the rate at which S is being produced? That rate depends of course on CS, but if it were in the absence of an enzyme, for example, it would be a first order in S, or it could even be a second order in S, but the way this reaction is written over here, it would have been a first order reaction in S, right. But as it turns out that when you have the enzyme, the kinetics of the process is altered, and what you have is known as a Michaelis-Menten kinetics. It is not a first order or a second order or a zeroth order or any kind of that, and the expression for the Michaelis-Menten kinetics, and I will do a summary of that, go back to it again in tomorrow's lecture. What happens is that this rate of reaction Rs is given as R max Cs over Km plus Cs. Now, R max being the maximum rate of reaction, Cs being the concentration of the substrate, Km being the Michaelis constant. The reason, I mean, this is so popular and so important is that it turns out many of the biological processes that are catalyzed by enzymes follow this reaction kinetics, and Km is known as the Michaelis constant, which is the way it's evaluated is that we keep measuring. So this is a plot, for example, of Rs versus Cs, and we keep measuring the values of the rate at different values of concentration. And when the value of the rate reaches a maximum, it saturates out. So this is how the graph looks like. So at very low values of Cs, the plot has a linear nature, and if I go back to this, at very small values of Cs, if I put this back into equation 1, what I find is that, so Cs I can neglect in the denominator, whereas Cs stays in the numerator, and if I go back, if I use this on equation 1, what I find is Rs turns out to be R max Cs over Km, and this is a first order reaction because Rs varies directly with Cs. Okay. Now at very large values of Km, Cs is much larger than Km. Okay. at very small values of Km, sorry. Cs is much larger than Km, as a result of which Km is goes away from the denominator, Cs stays in the denominator, and Rs is R max Cs over Cs. So, Cs cancels out and you have Rs equals R max. Okay. So, this turns out to be a zeroth order reaction. Now, when this is zeroth order reaction, what this means is, what does a zeroth order reaction mean? It means that the concentration is independent of the reaction rate is independent of the concentration. Okay. So, as a result of that, R max is just a straight line parallel to the x axis. So, these two give me the two bounds for the reaction order. So, at small concentrations of Cs, the reaction order is first and it is linear. At very large concentrations, the reaction order is zeroth and it is parallel to the x axis. So, for all concentrations in between these two, the reaction order is going to be in between the zeroth and the first order. So, the Michaelis-Menten essentially. So, if we are to evaluate the order of a reaction, so the Michaelis-Menten turns out to be an reaction of order between 0 and 1. So, as compared to if the enzyme was reacting directly, it would be a first order reaction. So, I think we will stop here today at this point, and we can continue with the kinetics of the process, more detailed analysis of the kinetics of the process, which is the analysis of the Michaelis-Menten kinetics, and I will kind of come back to the Michaelis-Menten to start with. So, because this is a very important thing and we need to understand this very clearly, the way the kinetics looks and what is its role before I go and analyze this a little further. So, we will do this in the next class. So, I think I will stop here. And so, what we have essentially studied is we have understood what enzymes are, we have defined enzymes, understood their function and specificity. We have understood the biochemistry a little bit and how the substrates go and bind to the active sites of the enzyme. We have looked at structures of enzymes, of a few enzymes. The human P50 enzyme is on your right, the catalase, and the glyceraldehyde 3-phosphate dehydrogenase enzyme is there also, and those things. And then we have looked at the thermodynamics of enzyme and how it works, and looked at the basic kinetics and the Michaelis-Menten kinetics of enzyme, and how what is the relationship between the rate and the concentration. So, we will stop here and we will continue with the details of the Michaelis-Menten kinetics in the next class. Thank you.